The second idea we're going to talk about in this section is called composition of functions, and this is probably a new idea for most of you. Now, composition of functions is just a different way to treat functions. We're not adding or subtracting or multiplying or dividing them like we were in the last video. What we're doing here is we're taking one function and we are making it the input of a second function. And actually, if you want to get really crazy, you can have several different functions that you compose together. So it doesn't just have to be two, but two functions is what we'll deal with most often. So first of all, let's talk about notation. There are two ways to write that you intend to use a function, or excuse me, a composition of functions. One way is to say, is to write it like this. And it looks a little weird, I know. So we read this as g of f of x. And this is just a little open circle right here in the notation. If you take a look at your book, you can see what it's supposed to look like instead of my sloppy handwriting. So that's one way to write a composition of functions. The other way, which is the way I actually prefer to do it, is to write it as g of f of x this way. So it's a little bit easier to see that our function f of x becomes the input for our function g of x. This might sound a little bit weird, but let's do a couple of examples and hopefully that will help things be a little bit more clear. So let's say we have these two functions. F of x is x minus 5 and g of x is x squared. So first of all, let's say that we want to evaluate g of f of x, like I just wrote on the last slide. I'm going to write the notation up here in both ways, just so you get familiar with it, but you certainly don't have to write out both versions. Just pick the version you like and use that to indicate what it is that you're evaluating. So g of f of x looks like this. So what this is saying again is we're going to take our function f of x and we're plugging it in to g of x. So I'm going to write this out step by step. You don't necessarily have to write out all the steps when you're doing this. But what we're saying again is, since f of x is x minus 5, that's what we're going to plug in every time we see x in g. So if g of x equals x squared, and f of x equals x minus 5, that means g of x minus 5 is x minus 5 squared. And of course, since you are multiplying those two binomials together, that would be x squared minus 10x plus 25. So that is the value for our composition g of f of x. Now let's say you wanted to find the composition of these two functions, but you wanted to do it in the opposite order. Instead of finding g of f of x, you wanted to find f of g of x. So in that case, using our notation, we would just switch the order. The f would come first, f of g of x. And again, I like this second version of the notation a little bit better because it tells you where to start. Whatever function's on the inside of this notation on the right, or whatever notation is on the far right side if you're using the notation on the left, that's the function that you start with, and then you plug that function into either the outside function or the leftmost function, depending on what type of notation you're using. Okay, so if we want to evaluate f of g of x, in this case that means we're plugging g of x in first, so g of x is x squared. And then for f of x, wherever I see an x, I'm going to plug in x squared instead. So that means that our composition f of g of x is x squared minus 5. So the order does matter. Notice that f of g of x, which was x squared minus 5, is completely different from g of f of x, which was what we got down here, x squared minus 10x plus 25. So that does mean that the composition of functions is not commutative. Again, that means that the order does matter. I want to do just one more example with you all using these same two functions just so you get a real sense for what's going on. So let's say that instead of just trying to find the overall composed function, we want to evaluate a composition of two functions for a certain value of x. So let's find g of f of -2. So again, because f is on the rightmost side of our notation, that means we're plugging -2 into f first. So that's the same thing as saying we're evaluating g of f of -2. Well, if I plug -2 in for f, that's going to be -2 minus 5. So that means we're evaluating g of -7. And then when we plug -7 in for g, we're evaluating -7 squared, which of course is 49. So there's g of f of -2. Now let's say that we wanted to evaluate f of g of -2, just to show you one more time that composition of functions is not commutative. So this is f of g of -2. So that means we plug -2 into g first. So that means we're doing -2 squared. -2 squared is, of course, 4. So that means we need to evaluate f of 4. And if I plug 4 in for f, that means we're evaluating 4 minus 5, which is -1. Now, on the last two examples, these last two slides that I did, I started with our original function definitions to get our answers. Again, we got a value of -1 for f of g of x, and we got a value of 49 for g of f of x. But earlier, on the two prior slides, we had already come up with definitions for g of f of x and f of g of x. So if we had wanted to, we could have just started with these definitions and plugged in our value of -2 in for x to come up with our solution. So let's make sure these work out. So if I plug -2 in for x here, we get -2 squared, that's 4, minus 10 times -2, that's 20, plus 25, and 4 plus 20 plus 25 is 49, which is the value that we got for g of f of -2 on this slide. And then also, if we had plugged -2 in for x here, we would have gotten -2 squared minus 5, which is 4 minus 5, which is -1, and that's the value that we got for f of g of -2. So there's two ways that you could do this. You could either come up with the overall, formula, you could call it, for the composition and then plug in the value of x that you're interested in, or you could just go ahead and start plugging in the value of x that you're interested in and evaluate it that way.